Okay. So we are working on multi-stage finance problems. Here's a few that you sent me from the homework. And I've written some things out, but I've covered them with the formula sheet, so you can't see what I've written out. So we can talk about first what you think we should do. So on number 2, it says suppose you invest 140 a month for 5 years into an account earning 8% compounded monthly. After 5 years, you leave the money without making additional deposits in the account for another 25 years. How much will you have at the end? So here's the formula sheet. What are your first thoughts on what formula you would use, or are you completely, do you kind of feel lost?
Because we're adding money and it's increasing, it should be the A equals E and then 1 plus R over K.
Okay, so yeah, sounds like yeah. So the first few things I want to have people pay attention to here is if you're investing multiple times or just one time. And this is 140 a month. So that's multiple times. That's going to be one of these two formulas if it's multiple times. If it's just one time, a one-time investment, that's when we use just the more simplified, kind of a simpler looking formula.
Right.
So that's one thing we want to look at. And then if it's compounded, you're always going to have these the same for this class. If you're depositing per month, you're going to be compounding per month. So you can count on that. If it doesn't maybe mention how much is compounding, you can assume it's the same as how many times you're depositing a month or a year. Okay, so yeah, and then if it's an account that's increasing in value, this is always the way I remember it, and I've sent that kind of tip out in announcements. But if it's increasing in value, we're going to use this big long formula with the positive exponent in it. And if it's decreasing in value, we'll do a few of those. We're going to use the big long formula with the negative exponent. So that's the way I remember which one to use.
Okay.
So you're right. We were going to use the one right here. And we're just going to put, so you'll have to know what each variable represents. D will be 140.
Right.
R, we got to change it to a decimal, so 0.08. K is the number of compoundings per year, because the interest rate's given in an annual. It doesn't really say annual, but that's what it is. It's the APR. So everything's in terms of years. So K will be how many times it's compounded per year. So that'd be 12. T would be 5. And then we kind of stop the problem there. We're not going to worry about the second after you leave it for after 5 years. So we want to figure out after 5 years how much money we will have, because then we're going to use another formula, and that's where it becomes a multi-stage finance problem. We got to kind of split this into two parts, because I just want to know, okay, if I'm doing 140 a month, 5 years, T equals 5, 0.08 is the R, K is 12, figure out what that is first. So we got my pointer here. Move this down. So that's what I did right up here. I put all that stuff in that formula right here. If you can see, and figured out what that was. So I want you to practice right now. And if you're watching this video, pause it and use your calculator to see if you get the same answer as me. Because I think putting it in the formulas half the battle. The other battle is putting in your calculator the right way. And so on a test, definitely make sure you write out your work, because then if you put it in the calculator the wrong way and get a wrong answer, at least I'll be able to see that you used the right formula. Whereas if you wrote nothing and just did it all in your calculator and then got the wrong answer, I wouldn't be able to give you any points, because I wouldn't at least know that you used the right formula without having you shown anything on the paper, if that makes sense.
Okay.
So I always recommend typing it in multiple steps. I don't know if you're trying it right now. I would do, with order of operations, I would start inside parentheses first, deep within the parentheses here. So I would do 0.08 divided by 12, hit enter, plus 1, hit enter, raised to the 60th power, hit enter, minus 1, hit enter. Like, that's the way I do it, is multiple steps. Times by 140, hit enter, and then divide by parentheses 0.08 over 12.
Okay.
Let me see if I can find. real quick. I have, I don't know where it went.
Well, shockingly, I did enter that in the calculator correctly.
Oh, good. Perfect.
That's been half my battle as well.
Yeah, so always check that. I want to, yeah, I had a, it's been a few semesters since I used it. So I don't know. I had like a virtual one I could, but I don't remember how to pull it up. I had one on my computer I could pull it, but I don't remember how. Oh, here it is. I forgot it was pen. Yeah, so you probably have something like this. I kind of verbally said it, but this is seriously what I would do is just do it in multiple steps. This is, unless you're confident about how you type in parentheses, then you want to do it in multiple steps, because even just missing one parenthesis could make your whole answer wrong. So 0.08 divided by 12 plus 1, hit enter, raise to 60. I'm going to minus 1 now. I'm going to times by 140. And divide by parentheses here, 0.08 over 12. And there it is. Okay, so that's after 5 years. Now we're not done with the problem yet, because we got to say, okay, now if we leave that money without making additional deposits in the account for another 25 years, how much will we have at the end? So what do you think about, what are we going to do now with these formulas?
Where I'm trying to get stuck, I want to say it's a payment. So on the sheet that I submitted from one of the announcements, if the account compounds continuously, I'm not sure. So the A equals PE over RC.
So if it was continuously, that is the one. You're right about a few things. Yes, it is now a single deposit. We're considering it that money. We're not continually now putting in 140 each month. We're just leaving this single amount that we just found on the end of the last problem. And but we're leaving it in the same account it was in. So it's not continuously compounding. We're going to assume it's the same as it was. It's 8% still compounded monthly. So if it's continuous, we'd use the one with the E in it. We're going to use, though, this A equals P 1 plus R over K to the KT.
Okay, so that was the next one that I would try.
Yeah. So, I might have messed up here with the, okay. Oh wait, that's right. Okay, so I'm gonna take that amount I just got, 10,28676, and I'm going to put it in this formula down here, if you can see it. A equals P 1 plus R over K to the KT. So this is our P now. This is our principal. We'll do 1 plus R. R is the same rate as before. It's 8%. Still compounding monthly to the, okay, and then it said 25 years. So 25. And then we'll figure out what that is. So let's see if I can do it up here. So again, I would do 0.08. Sometimes this thing times out. I don't know when I close it how to read. Okay, hold on. Okay, so we got 0.08. Well, it looks like I can type it in. Divided by 12. And then add that. Oops. Add that to 1. Raise it to the power. We're going to make sure you do it the correct order of operations. So inside parentheses first, then exponents, and then multiply it with the 10,000 loss. So I'm going to raise it to the 12 times 25 power. And then times it with 10,000. So we should get 75. Hold on here. Where did it go? 75, 506.23. Is that what you got? If you tried it? Are you there?
Yeah.
Okay.
That's what I got. So when I was first studying this one, I don't know why I thought, but I thought that it was continuously, but every time I worked through these, I kept getting different answers, which I think was the calculator problem.
Yeah, it definitely could be a calculator problem. So what do we do? Is our final answer 75 for the whole problem?
Yeah.
What do you think? So that looks like it. We just did our calculations right, but we always want to look back and see, do we need to add anything together? So like this 10,000 from before, do we need to add that to our 75 or do we not need to? So since we took this 10,000 from before and we're actually putting it in here and it was the one compounding. Yep, that's our final answer. I just always like us to think back and check because there's a few of them down here where we're going to have to take our two parts of the problem and add them together to get our total. But looks like that should be right. Let me see. I have your, I'll just leave it here. But I think that should be right. I'm going to have to pull up your homework and see if that.
Other screen so I can type it in and find out.
Yeah, if these, as long as these are the same numbers as what you were done with before. Sometimes if you get a new problem, the numbers will change.
And I think that's what I did is I took screenshots of exactly what we were working on and then copied and pasted.
Yeah, I think I have it actually right here too. Is it number 2? Looks like your numbers might be different though, actually, now. I don't know if you've tried a different problem. Because this says 160 for 6 years. On years. Anyway, we'll go back. Let's go to number, or we're not even done with it, right? There's another part. Suppose instead, yeah, suppose instead you didn't invest. We'll keep going with these numbers, I guess. But suppose instead you didn't invest anything for the first 5 years, then deposited 140 a month for 25 years into an account, 8% compounding. So how much would you have at the end? So now, again, we're back to a multiple deposits type problem where the account is growing in size. So we're going to use this formula down here again. And let me just move this away, and so we're going to do 140 a month, 8% interest, compounded monthly, this time for 25 years, and that's our formula. And if we type that in, I actually have a little cheat sheet Excel. Let's see if I can pull it up. Where is it? So I made this myself just because I do so many problems with students, just to save time on typing it in the calculator. Where I can then put all the values in and the Excel will calculate it for me. So if I do that for this one, let's see, we want the one with the positive. Our D would be 140. Our rate is 0.08 monthly, and it's for 25 years, right? So this just calculate that for me. It looks like it should be, and you can verify it with your calculator, but it looks like it should be 133. Oops. $133. It doesn't like when I switch back and forth, but you can see the answer there. 133, 143, and 70 cents.
Okay. So no, I think in that one, that's I was missing the one step in the last part. That makes a lot more sense now.
Okay.
Question.
So this person, I think it's helpful to reflect on it too, on the power of the compounding interest here. This person deposited 140 a month for 25 years. So let's think about how much they actually put in. They put in 140. So I'm going to do 140 on my own calculator over here times 12 times 25. Right? So they've put in 42,000 of their own money. And it turned into 133,000. What was it? 133, 143.
How much it grows, and you don't have to do anything for it.
Yeah, and this is a pretty good interest rate if you think about it. Like 8% is pretty good. Sorry, I keep forgetting what that is, but it's about 133,000. So they put in 42 of their own, and it grew to 103, which is pretty good. But even better than that, if you think this person here, they only put in 140 for 5 years. So 140 times 12 times 5, they only put in 8,400 of their own money, and then they just let it sit there. After only putting in 8,000, it grew to 75.
Yeah.
Because they didn't put any more additional $140 deposits in for the rest of the 25 years. And they still got pretty high, 75,000. I mean, it wasn't as high as making $140 deposits for 25 whole years, but because it had that value of time of 25 years just to grow, it got pretty high up there. Okay, let's do number 3. Oops. Okay. Trying to hide. I gotta take this and hide it. Okay, so number 3, you want to be able to withdraw 25,000 from your account each year for 30 years after you retire. You expect to retire in 15 years. If your account earns 6% interest, how much will you need to deposit each year until retirement? So it gives you all the information really quick. It feels like maybe there should be a one-step thing to figure this out, but definitely there's multiple steps here. We got to figure out first, kind of have to think backwards. How much needs to be in the account at the beginning of your 30-year retirement to be able to withdraw 25,000 a year? So think about what that account would be doing over time. We're thinking about the retirement time period. Is that account increasing over time? Or is that account decreasing over time?
Because we're thinking backwards, and at the beginning is going to be increasing.
Well, we're thinking backwards as in we're old now. We're in retirement age, so we're now pulling the money out. We want to think about that first before we think about putting the money in towards retirement. Because we need to know how much is needing to be in. Let's say in 30 years you're 60 years old, and we need to know how much needs to be in the account when you're 60, ready to start withdrawing. Hold on, I said it wrong. You expect to retire in 15 years. So let's pretend you're 45 right now. We're thinking ahead to 15 years in the future when we're 60, and we're about to retire, and we want to be able to pull out 25,000 a year for 30 years till we're 90 years old. So we're thinking in that time frame right now. We're thinking, okay, we're 60 years old. How much needs to be in the account right now to be able to pull that out? Because we don't need all the money in the account right when we're 60, right? Because it's going to continue to have compounding interest. So if you think about $25,000 times 30 years, I mean, that's $750,000. But we don't need $750,000 in the account when we're 60 years old, because we need a lot less than that, because we're not pulling it all out at once. We're only pulling, oh, did I say 20? Yeah, we're only pulling out 25,000 a year. Does that make sense?
Yeah.
So that's where we're at right now, is we need to think about the retirement account that's decreasing in value as our first step. We're not going to think about saving towards retirement as our first step, even though that would be the first step in real life. Like, like to think about an account that's increasing in value so we can get this money in there. We're actually going to figure out this problem, have to start at this stage where we're thinking about the retirement account that's decreasing in value. So we're going to start with this bottom equation in the formula sheet with the negative exponent. And we're going to take that bottom equation, and I'll just move this down. So there, we're going to put the 25,000 in the D spot of that. If I can get it all on the same screen. Okay, so I'm looking at this bottom equation down here. I put the 25,000 here in the, I guess it's called W, the W spot. 1 minus, here's our interest rate, 0.06. This is compounding yearly because we're pulling out. It didn't tell us, right? It didn't tell us how much it's compounding, but because we're withdrawing from the account just once per year, we're going to assume the compounding is the same, because that's how all your problems will be. So K is 1, K is 1, T is 30, because we're going to be pulling out 25,000 for 30 years. And then R is 0.06. How do you feel about that?
Yes, that's good there, because I was trying in the beginning to take, I was confused with the 30 years and then you expect to retire 15 years.
Yeah. So that's going to be our second part of the problem, the 15 years. But this is just the account that's decreasing in value, the retirement account where we're pulling out 25,000 a year. So we want to know, if we do that, how much do we have to start with so that we can pull out 25,000 for 30 years? How much do we need to start with? And that's what we're solving for here, is P. So if you want to take the time to put that in your calculator, or pause this if you're watching this video. When I put it in mine, I got 344,000, about 120.78. That means even though we end up withdrawing 25,000 for 30 years, so we times 25,000 with 30, you get 750,000. We end up pulling out 750,000. The day we retire, we only have to have 344 in that account, because over the next 30 years, it will continually earn interest, which will allow us to withdraw 30,000 for 25, or 25,000 for 30 years. Getting those mixed up. So that's how much needs to be in the account on the day we retire. Now, how are we going to save that? Now we're thinking back to, okay, now in our saving years, how are we going to save $344,120, So that's what I mean by thinking backwards. We think first of the retirement age, how much needs to be in the account then. So we look at the formula with the negative exponent first. Now we're going to look at how are we going to save for that. So we're going to go now with the formula with the positive exponent, because now we're thinking of an account that's growing in value over time. And we let A equal 344,120, that amount we just got in the last screen, the last part of the problem. We want to be able to save this amount. So how much do I need to put in monthly to be able to save 344 in 15 years? And that's what I'm going to solve for now, is D in this equation with the positive exponent. Everything else is going to be the same. 0.06 for the interest rate, compounding annually, so 1. 15 years this time is the T value. And we solve for D. And that's kind of tricky when you're typing that in your calculator. because I would probably, let me just kind of walk you through what I would do here. Is I would figure out what this number is first as a decimal. So let's see, 1.06 raised to the 15 power minus 1. So that's this number here is, as a decimal, is 1.39. That's a decimal, 1.39656 about. And then I could divide that with 0.06. This 0.06 down here. And then I'd have 3, 4, 4, 120, 78 equals D times what I got when I took 1.39 divided by 0.06, which is 23.27. And then you could just divide both sides by that 23.2759. You want to go out to lots of decimal places with these so that your final answer can be as accurate as possible. So don't round to 2 decimal places until you're at the end of the problem. Mm-hmm. Does that make sense? Are you typing it in?
Yeah.
Okay. So you should get 14,784. About. That will be the yearly deposits that you'll need to make for 15 years. And again, it's kind of cool to reflect on this. So you're putting that much in every year for 15 years. So if you take that 14,784 and times it with 15 years, you yourself have only put in 221,000, about 221,765. That's the amount you've put in, but it turned into 344 by the day you retired, 344,000. Even though you only put in 221, it turned into 344 because of that compounding interest over the 15 years that you were saving. And then beyond that, you were able to withdraw 25,000 for 30 years, which is 750,000. So with only putting in 221, you were able to withdraw 750 over the course of your retirement. So again, pretty cool to reflect on that. Okay, let's do our last one here. Unless do you have questions for me on that one? If that makes sense?
No, that makes sense because where the 30 and the 15, I was just making it more complicated than it really needs to be. I was trying to use 15 in the beginning
In the first part, yeah.
Because in my head I'm thinking, okay, well, I need it. I'm retired. I'm working 15 more years. So I was trying to do 15 instead of 30, which obviously you threw that part. You threw out the entire question.
Yeah, so I'm glad you're showing me because I'm sure you're not going to be the only one who makes that same mistake. So yeah, separate the time periods into, am I in my retirement stage or in my saving stage? So if I'm in my retirement stage, use the time period that you're going to be retired for, and that's going to be the formula that's going down in value, so the negative exponent. And then once you find that, we'll go to the saving stage. We'll use that time period for the t, and we'll use the exponent that's positive, the formula with the positive exponent. Okay, and the last one, number 5. Chad's making monthly contributions of $490 to a savings account, which pays interest 6% compounded monthly. Right after Chad makes his 60-second contribution, the bank changes the APR to 6.3%, and Chad makes 55 more contributions. What's Chad's balance right after his last contribution? So what do you think on this? What formula would you think to use on this one?
So we're going to use the increasing long positive exponent long formula.
Sure.
And I want to do it twice. So we do it 490 at the 6%, and then my head I want to do it again, but it's a 6.3%. But then I kind of get lost from that.
Yeah, you do. You're great. So you perfect formula that you chose with the positive exponent down here. 490 as our monthly amount that we're putting in. 6% is our interest rate. I think the hard part on this one that to figure out might have been what am I going to put in for the KT, because K is usually the number of compoundings per year, how many times you're depositing, and then T is the time value that it's in there. It didn't tell you a time value, it just told you how many contributions. So that was the tricky part. Now usually you can take your time value, like if it's a 20 years, and it's compounding monthly, we would take 20 times 12 to figure out this exponent up here. That's what the formula tells us to do. K times, so the number of compoundings per year times the number of years. And that tells us this exponent up here, which basically is like telling us the number of month that we're on, if it's compounding monthly or, so in this case it's monthly. So if it's the 60-second contribution, I mean, you could think of this a few different ways. I just put 62 up there in the power spot. But if you think of it, the 62 contribution and its monthly contributions, you could do 62 divided by 12, and you could think of that's a time value of 5.1666667 years. So let's see, 0.1. Anyway, so you could put the time value of 5.166666667. I mean, you want to go out to lots of decimal places, and then times by 12, or you could just use the 62 that they told us. So I think that might have been the hard part there, because maybe some people wouldn't be sure where to put the 62, and that's what that power is telling us, is what contribution number we're on. So we put that up there. And so when I put that in my calculator, I got 35.
I was doing 62 times 12.
Yeah, so that would be too big of a power. Yeah, because 62 times 12, it's not, that would be like 62 years, right?
Right.
And we want the 60-second, after the 60-second contribution. So I need to find out how much is made in this time period after the 60-second contribution, and then do it again with this higher interest rate. And then I was doing this before you came, and I need to make sure I get this right answer, because I think I 0.063 over 12. Oh, and hold on, let me make sure. I think here's my problem, that I didn't put a parentheses. See that here's, I was kind of going too quick before I started this. I need to make sure that I okay, I need a parentheses around these, right? I need to minus the 1 before I multiply with 490. So I think actually my answers, it might be wrong. I was thinking that they looked wrong, and then I was going to try to figure out where it was. Because look at the formula down here. Down here, see that? We minus the 1 inside the parentheses before we times by that D amount. So I definitely needed that parentheses there. I wouldn't want to times by 490 too soon. So 0.06 divided by 12 plus 1 raised to the 62 power minus 1 times 490. I'm hitting enter in between all these. Divided by 0.06 over 12. Okay, so maybe that one was right. Minus 1 over 490. Okay, that actually what I got the second time, so I'm going to go with that. But maybe on my second one, let me see if that was right. that what you got too?
No, I got something different. I think I typed it in wrong again.
Okay.
Doing it here.
We'll try. Let's see if we got. Let's try the second one. Okay, I'm gonna talk as I type this in. I'm doing this second one down here. I'm going to do 0.063 divided by 12, hit enter, plus 1, hit enter, raised to the 55 power, hit enter, minus 1, hit enter, times with 490, hit enter, then divide with parentheses 0.063 over 12, hit enter. Okay, those are the same things I got before. All right, well, when we add those up, that should be our final answer there. We have, is it still 490? Yep, okay. So that's what he gets in the first 62 contributions is what it turns into. And then okay, I'm thinking about, that's how much we have to add one more thing, and that's why our answer, I was thinking it doesn't sound quite as big as it needs to be. Okay, so and I want to see if you can recognize what we need to do beyond what we've done. Okay, this is what we get after the first 62 contributions. This is what we get after the second 55 contributions. Are we missing any amount of growth in there? This amount here, after the first 62 contributions, continues to grow, right? And I don't think we've accounted for that yet. We just kind of, if we just added these two together as they were, we would be finding out, it would be like us saying that this $35,000 stopped growing at the end of the 62. But did it really stop growing? Or is it continually growing in that same account?
No, it's continually growing.
Yeah.
It's just his new deposits.
His new deposits are growing at a faster rate. Yeah. So that's what we did here with the 31,000. But this 35 also continues to grow for that 55 unit time period. So we need to take this and consider it like a one-time deposit. So this formula down here. And we'll take that amount because it's continually growing in the account at the same time. So we'll take 35,512.49 and 1 plus, now it's growing at the 0.063 interest rate, right? Over 12. Now to the KT. KT is always supposed to tell you how many time periods. So we're going to use that as our 55. So how many compounding, because it didn't tell us a time period, it just told us 55 more contributions, which we assume is 55 monthly contributions. Yeah, so 55 months. But since this is in units of years, we just put the 55 up there. And then let's see what that is. 0.063 over 12 plus 1 times 35. Let's see. 0.063 over 12 plus 1 raised to the 55 times 35, 512. So that turns into 47,364.79. So do we add all three amounts or do we just add two amounts?
We just added two amounts.
Yeah, just the two. Good.
And then the
Yeah, perfect. We already included the 35 in there. This is what it was at the end of the 62 contributions, but then it continued to grow into the 47. So we've already accounted for that. So we only add these two together. Good. And then we get our final answer of about 78,514, which I think is the right answer. So I think I have it pulled up here. It's number 5. Yeah, 78,514. There we go. I can give you the credit on that one since we just did it together.
Okay, so I'm going to work through it. Anyway.
But you can work through it with the new numbers, but I'll just give you the credit for that one.
Yeah.
Okay. Sorry, that one kind of, I hadn't finished that one all the way when we started. I was just getting there. So hopefully that makes sense too as we talk that through.
No, that's awesome because, like I said, some of these, I guess I was just thinking in the wrong way. Like, what makes sense in my head doesn't always make sense in the way that I need to do this. And I think that's where I get a little confused. And then, like I said, I'm kind of excited that we get the formula card for the exam because I know we're using the formulas. It's just a matter of figuring out, what's W, what's R, what's A, what's E, those types of things. So just knowing exactly what numbers to plug in and where, I think was kind of where I was struggling a little bit.
Yeah, as well. You're right on. That's where every student's going to struggle. Yeah, that's where every student's going to struggle. So make sure you're studying this formula sheet on which one to use and when, and which variable means what, and exactly. And yeah, just the more practice problems that you can practice, the better. So yeah, thank you for asking these questions, and thanks for allowing me to record this. And
yeah, no problem. No, I appreciate your help and be willing to. I know you said you're an early bird, but get up at 7 a.m. and then
yeah,
an hour walking through it so that I can understand. So I really appreciate it.
You're welcome.